right, thank you, Luke, and good day, everybody. As Luke mentioned, my name is Vincent Britz, or Vince, and yeah, as Luke introduced, I'll be talking about doing dynamic pipe stress analysis in Flownex today. So just to kick it off, I'd like to give a brief overview. The presentation will begin with a short introduction of Flownex, talking a little bit about what the software is and where it's used. Then I'm going to talk about some of our common pipeline components, so some of the typical components we use in modeling these large piping systems. Then I'll demonstrate an example where we use Flownex and RAW2 to do dynamic pipe stress analysis. Next, I'll talk a bit about a boiler tube failure analysis. So this is done with Flownex and ANSYS Mechanical. And then lastly, I'll talk a little bit about some additional applications of the software. All right, so Flownex itself is as Luke mentioned, a one-dimensional flow and two-dimensional heat transfer network modeling software package. So basically what that means is it is almost a CFD-style software package where we look at modeling fluids in a traditional CFD environment. However, the building blocks are one-dimensional. So our networks tend to be, or our simulations tend to be networks rather than three-dimensional geometry. These networks are then solved with a pressure correction method similar to CFD, and we use conservation equations of mass, momentum, and energy as our governing equations that we then solve with our differential equation solvers. The software itself is able to do simulations in both steady state and in transient, and includes many different types of fluid models. So we have fluid models for liquids and gases in the sense of compressible and incompressible models, as well as more complex models like two-phase fluid models or mixture models for gases or liquid and gases if you're looking at perhaps modeling combustion. And then also some further models for slurries, for both settling and non-settling slurries, taking into account shear rate dependent viscosities. The software itself also includes a bunch of other analysis tools. So we have a designer. This is similar to the goal seek inside of Excel. You provide target values for results that you would like and a set of inputs that Flownex can vary, and it then varies these inputs until it achieves those particular results. Our optimizer works in a similar way, except instead of a target value, we either look to minimize or maximize a particular value. The sensitivity analysis functionality is also quite useful in trying to better understand the system and understand the inputs. It can be configured in two ways. One using a parametric table where the user specifies different cases they would like to test, and the other one is using a Monte Carlo analysis where the user just selects a distribution function and Flownex generates random data and calculates results for that. So we can generate basically a response surface for a particular result as a function of many different variables. The software itself is developed within NQA1 and ISO 9001 regulations. Basically what that means is that the software is under very strict quality control criteria and is at the level that it can be used for safety critical calculations in the nuclear industry. So higher levels of verification and validation go into the testing of the software and the development of the software itself. The software has been around since 1986. It started out in the nuclear industry, but has branched out from there into many other industries. Okay, so here are just a couple of components that are relevant to the piping industry, or to just general process modeling. We have just these four main categories that I'll talk about. The first one being valves. These include a lot of generic models, be it say a butterfly valve or a globe valve, with empirical models for these particular components, right through to different valves such as pressure relief valves or blowdown valves, where the user can look at modeling these type of components, as well as more generic models such as an ANSI control valve. In this scenario, you simply specify some basic geometry for the valve and then choose a characteristic for it, be it a linear valve or perhaps an equal percentage valve. And then Flownex uses the relevant theory to model the pressure loss behavior through that component. All of our valve models, along with our flow components, also take choking into account, so that you can also consider that when designing the flow inside of your system. Our bend components are for both rounded bends as well as mitre bends. They employ ESDU correlations, and the bends themselves also have results for the forces or the reaction forces that are required to support these bends. These forces are a result of the pressure difference across the bend, as well as the change in direction of our velocity. So both of these are taken into account, and these forces are then made available in the results for these components. In terms of piping, we have a few piping models as well. Simple piping models where we can simply look to model primary losses with a catalog for secondary losses. I'll speak more about that in a second. Through to more advanced models where we look at insulated piping and heat losses to environment. We have other little models to account for additional secondary losses in the system, be it gradual pipe transitions or perhaps restrictions inside the system, RFS plates, and the like. And then the last one of these categories is then pumps. We have models in a similar way to the valves. We have pumps that can be specified to match existing pump curves. So if you have a delta P versus Q graph, or a pump chart for lack of a better word, this information can be directly inputted into Flownex, and this will be used to predict the pressure rise of that particular component. Alternatively, if you're looking at designing a particular system, we have components where you can simply choose an operating point, and Flownex will then predict the performance of that pump off its design conditions as well, using some pump scaling laws as well as some additional theory. In terms of the additional databases, our piping components has many other little plugins, perhaps, for lack of a better word, and they just provide the user with little databases that they can use to add secondary losses to their system, as well as a couple of other useful inputs. So what we see over here is a screenshot of our secondary loss database. In this screenshot over here, I'm just specifying the secondary losses for a screen inside of a pipeline. So perhaps there was a perforated plate with an area ratio of 0.6. This, according to the theory developed by Idealchick, has a secondary loss of 2.26. So inside of this little Excel interface, you can just insert the number of these components you have in a particular pipeline, and Flownex automatically sums all of these secondary losses together and adds them to the input of the pipe component. So it makes accounting for additional secondary losses inside of your system relatively easy. We also have a database for roughness values as well. So when you're accounting for primary losses in your pipelines, we have many different materials, and the user can then just select either a minimum, normal, or maximum value for these typical roughness values, and Flownex will then insert that as its roughness value when using for use in the primary loss calculations, perhaps Dashi-Wishbach in this case. And then lastly, we also have geometry specifications according to common piping standards. So for example, you might specify, say, a Schedule 6 pipe for size DN8, and in this case, you can simply select that as your option for your geometry specification, and Flownex will automatically populate the wall thickness and diameter variables from this. So it makes it relatively easy to take information from, say, a PNID and put that into a Flownex simulation itself. In terms of the force calculations, as I mentioned, we have forces from pressure differences. In this case, this is available on most of our flow components, so pipes, orifices, restrictors, etc. And then also forces from velocity change and our bends. So we're able to see the magnitude of these forces as well as the individual components of these forces. These become incredibly important in the analysis of the stresses on these particular pipelines. When it comes to importing geometry into Flownex, we have a couple of options. Building a network with hundreds of pipes can be quite tedious, so it's more convenient to import these networks. So we have a couple of different options in this regard. Common formats such as PCF and shapefiles are available, as well as importers from other codes such as AutoCAD's DXF files, as well as ANSYS connection files or ANF files. On the bottom left here, you can just see a simple screenshot of a shapefile that's been imported. This basically characterizes the geometry and will take that the geometry for pipes and bends and insert that into Flownex with the relevant diameters, lengths, as well as all the information for the bends as well. It can be displayed in an isometric view in 3 dimensions. This is just convenient for displaying some results. The system itself is still available in its traditional 2D view as well if you would prefer that. On the right hand side over here we have a this is a shapefile. The previous one was a PCF file. This one here is a shapefile. Basically it is a large gas pipeline, a distribution pipeline that's been imported into Flownex. the lengths of all the pipe components and nodes have been imported and automatically applied to the components on the canvas that you can see over there. And then basically all the user has to do in a situation like this is specify some information regarding what fluid is used, as well as some boundary conditions. But as far as importing all of the lengths of the pipes, elevations, diameters, for example, can all be mapped straight into Flownex. So it makes the construction stage of your model relatively quick and easy. Alright, so moving on to today's demo. Today what I'd like to demonstrate is a pipe stress analysis for a sudden valve closure. So the network that you can see over there is just a screenshot of what you would see inside of RAW2. We have a simple pipeline, a couple of branches, and some elevation changes with some bends and flanges. And what we'll be doing is simulating the thermohydraulics in Flownex and solving for the pipe stresses inside of RAW2. So I'm just going to jump across to RAW quickly. This is then the example that you've just seen. We had a chance to work with the RAW2 guys a while ago and developed an exporter for the geometry from RAW. So this makes it incredibly convenient in getting this information into Flownex. So if we simply click File, Export, and Fluid Flow Analysis for Flownex, we can actually create a file over here that will contain all of the geometrical information from this pipeline, which is then already in a format that Flownex can read. So we just save that. In this case, I'm just going to call it a file called demo. We can then move across to Flownex and import this file. So if we click our Import tab and then import RAW2, we can simply just navigate to where that file is saved and then open the file that I've just created. So when we open this, it opens a small configuration window. This just allows the user to make any modifications that they would like in the interpretation of that file. However, because we developed it with RAW2, all of the inputs that you see here are already correctly configured. So we can import that. What it's going to do is take that geometric information, create all the necessary Flownex components, and automatically specify the inputs for those components. So if I just scroll around, you'll see this network over here with all of its pipe components, bend components, any losses inside of the system, be it pipe transitions or secondary losses, are all automatically configured on these components, along with all of the elevations on the nodes as well. So for example, we can see the elevations have been specified, as well as geometry in the form of length or diameter, for example. Okay, so all that's necessary to actually solve the simulation is to specify a couple boundary conditions, specify a fluid that we'd like to use, and then to configure a transient simulation for the valve closure event. So just to save a little bit of time, I've just pre-configured that in this little network over here. It's an identical copy of what we had, just with some of the boundary conditions specified. I've created a little graph over here to display the pressure upstream of the valve. So the valve is represented over here as a secondary loss, and the pressure upstream of that is then going to be plotted on this graph over here. Let's just disable that. Enable that. Disable this. I'm just disabling the or the network that I just imported because I don't want to solve that. Okay, so over here I've configured an action inside of Flownex. This is basically an event that will happen in the transient simulation. This event at 0.2 seconds will begin to close the valve. We'll have a linear, the valve will close linearly, and it'll close at a rate of 200% per second. So basically closing in half a second. Using this information, Flownex will basically adjust the diameter value for the secondary loss, and this will then create the pressure wave inside of our system that we would like to export to RAW2. So to solve the simulation, we simply just need to solve steady state. So that's very easy, and then we can run our transient simulation. So as we begin to run the simulation, at the moment the y-axis is auto-scaled. You should see relatively small change there. At 0.2 seconds, we should have our valve begin to close. As that happens, the pressure just upstream of our valve begins to spike. This is happening due to the water column basically being decelerated, and as a result we have a pressure wave traveling through this pipeline. This pressure will begin to rise quite considerably, and Flownex will then be able to predict that. The solutions inside Flownex for both fast transients and slow transients, fast transients being events such as, say, a water hammer, and slow transients being, say, regular changes in valve positions for control purposes, perhaps, are all solved by the same basically by the same physics solver. So configuration for these transient networks is incredibly easy. Users just simply insert components, solve steady states, and then run a transient simulation. There's no need to go ahead and modify complex solver settings. The physics and maths is dealt with in the background, and the user simply just needs to worry about the specifications inside of the network itself. When it comes to viewing our results, we have many of these visualization components, but we also have additional interfaces for exporting. So if you would like to perhaps export this data as an Excel report, we have an Excel reporting functionality where you can actually extract data individually. All you have to do is simply click on a component, open the results section of that particular component, and you can drag and drop that information into the report, and that cell, perhaps if I dragged the quality, for example, to that cell, that quality will be mapped to that particular cell, and you can then simply copy and paste this information into Excel or open that individual Excel report for use later. This information can also then be converted to a CSV format very easily and used in other pipe stress analysis software. So perhaps you're using CESA2 instead of RAW2, and in which case you could extract all of your pressure information as well as any bend forces and put that into an Excel sheet, convert that to CSV, and use that as an import for CESA as well. Okay, so over here we can see our pressure wave. We see that rapid increase in the beginning, followed by a rapid decrease and a couple of oscillations before returning to a steady condition. What I'm going to do now is just save this information. During the import process, where we imported the geometry from RAW, it also created a configuration file. This file contains the definitions of the forces that need to be populated inside of RAW and the nodes that need to correspond with those forces inside of Flownex. So when Flownex creates a results file that RAW can then read, all of the force definitions are automatically populated. So this results file, if we look over here, incorrect place. If we just go back to RAW, we can simply import this results file. If we open loads, tasks, and then move across to our water hammer information, we can find a load function over time, and then simply just navigate to the location where this file is saved. So Flownex is saving a CSV file over here. This CSV file is basically going to contain all of the force information over time. You can see just a small sample over here, individual columns for time, as well as all of the forces that are populated from Flownex. We need to do a small amount of configuration to tell RAW exactly what the format of this is. So we just need to click the row with the load names, the column with the first force, and then the row with the first time step. And just like that, time steps not increase. Okay, that seems to be a mistake. This seems to be a small little problem. Let me just import this one instead. Okay, seems to be a small mistake in the file that I used. Let's quickly reconfigure it, click the row, the column, and the row. Okay, so that basically imports all of the forces for our stress analysis. We can then just confirm those forces and solve a simulation. So over here we just run our stress simulation, give RAW a couple seconds, and this basically calculates all of the stresses on the pipeline as well as all of the displacements. We can then move across to our results section and start viewing these results. So I'm going to view stress. Initially it's set up for displacements, so we can visualize the displacements in the system, and you'll notice that around 300 milliseconds we start to see quite large displacements in our system with the traditional oscillations you would expect from water hammer. We can even move across to a stress representation and start looking at what effect this is having on our material, and if there are failures in any of our particular components, say bends or T-junctions, for example. Alright, so just to recap, the raw simulation, all of that geometry can be exported into a file that can be read by Flownex. This file is then imported by Flownex. We specify some boundary conditions and configure our dynamic event that we would like to simulate. In this case, say this water hammer scenario. We then solve the network in Flownex. This information is written to a CSV file, which then is read by RAW and can then be used in its structural calculations. We can then view those results either as displacements or stresses, for example, and then do any further analysis on the system that we would like. As I mentioned, Flownex can also export to other data types, so we can export to Excel, and this can then be used as a CSV import to other pipe stress analysis software, if that is the software that you use. All right, the next thing I'd like to talk about is a boiler tube failure. So this is slightly different to your traditional pipe stress analysis in the sense that boilers are many tubes all connected in parallel. This is typically not an application suited to most pipe stress analysis packages, so we'll be looking at an ANSYS mechanical link here instead. The particular picture you're seeing over there is a photograph of a boiler from a company called Eskom. They're the electricity supplier for South Africa, and this is a photograph of the bottom section of one of their boilers. This particular failure is happening because of cyclic stresses inside of the boiler. So these coal-fired boilers have to have to change their load to follow the demand from the public. And as a result, these units have to go through these cyclic loading patterns. And this results in some rather large thermal stresses inside of the system and often leads to these boiler tube failures. So a tube failure is commonly just a small little hole that results in the side of one of these tubes and basically results in a loss of pressure in the system and a unit trip. This then results in quite a large amount of downtime and costs the company a lot of money. So as I mentioned, this all comes about due to the fatigue loading or these cyclic loads. And this graph over here just shows the typical ambient temperature profile during the startup of one of these boilers. So you can see that, in a coal boiler there are typically 3 stages. First a gas combustion, followed by an oil combustion, and finally the coal begins to burn. During these stages there are quite large temperature changes in the ambient temperature profile. And this creates those cyclic or those large thermal stresses inside of the system. So to properly understand this, the engineers at Eskom used a structural code, in this case ANSYS mechanical, and Flownex to simulate those particular flows inside of the boiler and calculate the stresses that result. So in this example, the plant drawings were digitized into CAD drawings and then used inside of ANSYS mechanical to create the structural model. This information was exported in PCF format and then imported into Flownex. So roughly 4,000 flow components were then imported into Flownex, and Flownex then solved for the flow and heat transfer inside of the system. This information was transferred to ANSYS mechanical and then used in the structural simulation. This led to quite interesting results. Basically, engineers were able to identify these high stress zones inside of the boiler and make small modifications to the geometry to minimize these stress concentrations and basically reduce the likelihood of the boiler tube failures. If you'd like some more information on this, I'd suggest you take a look at this. This work was all published in the Journal for Engineering Failure Analysis as well as Power Magazine. So perhaps just take a screenshot here or something if you're interested. The work was done by engineers by the name of Marius Buerta and Michael Hindley. You can find some more information there. Unfortunately, I don't have much time to discuss their work, but all of it is documented and it's quite interesting. Okay, finally I'd like to talk about a couple of additional applications. So as I mentioned, Flownex has a optimizer tool. We can use this for cost optimization in sizing our pipelines. So we have the Excel functionality built into Flownex, which allows us to take information such as the diameter of a pipeline and the power demand from a pump, perhaps. If our pump is specified with an electrical efficiency as well, we can actually get the electricity or the power required to run that pump. And using the diameter and this operating power, we can start developing basically an objective function for the total life cycle cost or the total lifetime cost of this particular pump and pipe arrangement. We can then perhaps use a sensitivity analysis or the optimization feature and look to minimize that cost over time and select the most appropriate size piping for our system. We can also look at analyzing failure events. These could be serious events such as pipe ruptures or just simply pressure relief scenarios, situations where we need to analyze flow rates and perhaps even stresses as well. We can also look at optimizing load changes. So Flownex itself has an inbuilt control module There's another webinar on that. I'd strongly recommend you take a look at that. It's available on our website. And using these control components, we can link the control simulation to the fluid flow simulation and start looking at the rates at which we change particular components, say valve openings, for example, or pump speeds, and look at optimizing these to ensure minimal stresses on our system as well as fast load changes to match the demand. And then obviously you can also use Flownex for flow validation studies. So if you're looking at designing new systems and just want to ensure that your flow is adequate, you can then use Flownex for the flow assurance or flow validation as well. Okay, so in conclusion or in summary, Flownex itself is an ideal tool for thermohydraulic simulations when you use it with dynamic pipe stress analysis software. The reason for this is we have many diverse fluid models. As I mentioned, models for gases, for liquids, for two-phase fluids, for slurries. It has a user-friendly interface and a robust transient solver. So we're able to build our simulations quickly and solve them in a very reliable manner with very little technical expertise required on the numerical solution side. Okay, that about covers it for today. If you are interested, feel free to contact us through the request a demo section on our website. If you go to flownex.com, you'll see there's a small tab for request a demo. You can then get in touch with us there, and we can either put you in touch with a local reseller, or we can discuss with you directly and showcase some more features of our software that are particularly relevant to your company.